So this is Med, Math, and Beyond Part 3, Drip Rates. This is where things get a little more complicated and can get confusing, but just like each of the other parts of drug dose calculations, we need to break it down to each of its component parts and try to keep it as simple as we can for ourselves. And there's some approaches that you can do that will help. A couple things to keep in mind when we're talking about drip rates is you'll see the abbreviation GTT or GTTS. It's a term that means drops. It actually comes from a Latin word, but that's drops per minute is equal to drops per minute. GTS per milliliter would be drops per milliliter, and you'll see references to both of those. And it's important to recognize that we have to pay attention to both, whether we're talking about the way a drip set delivers fluid, that's drops per milliliter, or the rate we want the medication to be administered, and that's drops per minute. There's a couple of types of drip sets that are out there, and we talk about macro drips or micro drips, also known as mini drips. And this is not macro and micro, we think big and small. It's not big or small in terms of the number, it's just the opposite. It's in reference to the size of the opening, the size of the little drip chamber that allows the drops to go through. So a macro will provide 10, 15, or 20 drops in order to deliver 1 milliliter. In other words, it's coming through a big open plastic tube, and 15 is the most common size for macros, especially in EMS uses. A micro, on the other hand, you can see comes through a little tiny metal tube, and it takes 60 drops in order to deliver 1 milliliter of fluid. Macro drips are used for fluid administration, and they flow much faster. Obviously, if it's 15 drops to get to a milliliter instead of 60, it's going 4 times as fast. Micro drips are used for precise delivery, such as drip medications. So we'll talk about the difference of those a little bit. So when we talk about 15 or 60 drops, we're giving fluid or we're giving meds over time. So the system is designed to correlate well to a clock. So we're set up to do 15 and 60 because that correlates again as to 60 seconds in a minute, 60 minutes in an hour, and 15s are 1/4 increments of that. We can use this to calculate our drops per milliliter, our drops per minute, our milliliters per hour, etc. So a micro drip, that 60 drops, means that 1 drop per second is going to equal 60 drops per minute. In other words, 60 drops is equal to 1 milliliter. So this tells us that if you're using a micro drip and you run it at 1 drop per second, you're going to deliver 1 milliliter in that minute. That's the equivalent of 60 milliliters per hour. So if you keep that in mind, it makes the math a little simpler. So another way to look at it is think about this as a clock representing 60 minutes, and we run this at 1 milliliter, 1 drop per second rather, 1 milliliter per minute. Over that entire hour, we're going to have delivered 60 mils. If we were to only run it for 15 minutes, we're giving 50 mils, and so on. A macro drop, 15 drops per milliliter, is going exactly 4 times that rate. So if we ran that same drip set at the same rate, we're giving 4 times as much fluid. So as was reflected on the clock here, if we run it for only 15 minutes at 1 drop per second, we're going to deliver 60 mils. If we run it for 30 minutes, 120, and so on. So you can see that the drip set you choose is going to determine the amount of fluid that's administered. You can also see why a macro drip is going to be much more suitable to delivering significant amounts of fluid. So we know a macro drip at 1 drop per second delivers 240 milliliters per hour. That would be a very conservative rate in most EMS situations. Fluid bolus or fluid administration situations in an EMS emergency, we typically want to give fluid much quicker than that. If you wanted to double that, you're giving 2 drops per second. That's going to equal 480 milliliters per hour, or 240 if that was your goal, would go on in 30 minutes. You double it again, it's up to almost 1 liter per hour. Any faster than that may be very difficult to count the drops. So if you're going to give more than if you want to give more than a liter in an hour, then you probably are going to run it wide open, meaning you open up the little roller clamp and what you see going through the drip chamber is just a continuous flow of fluid. At that point, you aren't measuring how quickly you're delivering the fluid, and you need to monitor the bag to see how quickly the fluid is running in and how much fluid you've administered altogether. Keep in mind that the size of IV catheter, the positioning of it, how high you have the bag, which affects gravity, and the pressure on the flow rate, all of those things can influence how quickly that fluid goes on board. And if you use a pressure bag or squeeze the bag, you can put it in even quicker. So it becomes a matter of just monitoring that flow and figuring out how much fluid you're actually administering. With medication administration, we use a microdrip set, and we use a roller clamp on the tubing to set an approximate flow rate by counting those little drops as they fall into the chamber. So we have the roller clamp. That's what's going to control. By rolling the clamp up, it releases the pressure off the tubing and increases the flow. Rolling the clamp down decreases the flow. And this is obviously a very primitive system. You're simply putting a little squeeze on the tube and you're varying the amount of squeeze as you move the clamp up and down. Understand that if you have a medication that requires precise delivery, we should be using an IV pump. We absolutely should not count on the method I just described and that we're going to calculate here for precise critical medications. Having said that, in EMS, we don't always have pumps. Some systems do, some systems don't, and we're expected as paramedics in the field to know how to come close with these calculations by calculating the drips and doing that. However, got to be aware that a lot of things can change the drip rate after you have it established. If you change the height of the bag, it changes the amount of pressure going through that tubing. If the patient moves their arm, flexes their wrist, anything like that can change how quickly the fluid is running in after you got it adjusted to what you thought was an appropriate rate. If the tubing gets kinked, it gets caught in a strap on your gurney, or it gets pinched between the patient and the side rail, something like that can change the flow. And there's any number of other things that might disrupt a nice flow of your IV. So you have to be aware that if you're using this method, you need to continuously monitor those drip rates and make sure that they're actually continuing to drip in at the rate that you thought they were, at the rate that you set it at initially. We talk about IV infusions. Another term for that is piggyback medication delivery, and what that refers to is that often you will have an IV in place, and rather than start an additional IV, you mix up your infusion, your pre-mixed medication, and you hook that into the existing line. That's where the term piggyback comes from. So for any IV infusion, we're talking about a quantity of concentrated medication is added to a bag of fluid, or in some cases it may be provided pre-mixed for you, where you have a bag of fluid with the drug already mixed into it and labeled on the bag that way. We need to know the total amount of fluid and the total amount of medication in order to determine the concentration. Remember, we talked about concentration is how much drug is in 1 milliliter of fluid. So each milliliter, for example, 4 milligrams per milliliter, 1600 micrograms per milliliter. I don't want to know how much drug is in 50 milliliters. I need to know how much drug is in each milliliter, because that's how our drip sets are calculated. So to get the concentration, I take the total drug that we have over 1 milliliter, and we'll use some examples of that. So lidocaine is commonly mixed by adding 2 grams to a 500 milliliter bag. So 2 grams is the same as 2,000 milligrams. So if I have 2,000 milligrams in a 500 milliliter bag, I can cross out a couple of zeros and figure out that I have 20 milligrams in 5 mils. Do my division there. That means I have a concentration of 4 milligrams per milliliter. And now that's a medication that I can work with. Dopamine is another drug, not as used as commonly in EMS these days as it used to be because there's some risk of dysrhythmias, and so we don't see it used as much, but it's a great one to learn and practice in drug calculations because it requires you to do each of the components that we're talking about here. So dopamine, typically you put 400 milligrams into a 250 milliliter bag. Not the only way it can be mixed, but commonly it's done that way. You do the math here, and that's 40 divided by 25. 40 milligrams is equal to 40,000 micrograms. Remember, milligrams and micrograms is a 1,000. It's simply a matter of adding 3 zeros to it. And the reason we do that is because dopamine is always dosed in micrograms. So I want to know how many micrograms I have, and in this case, I have 1,600 micrograms per milliliter. For future reference, as you're looking at these problems or looking at dopamine drug calculations, you will find that the majority of time dopamine is going to be packaged in this concentration, 1,600 micrograms per milliliter, which works well for some shortcut methods I'll talk about later. So the next step of this is figuring out drugs per minute. So when you have a dose that isn't just give 5 milligrams, but rather it's you need to administer 2 milligrams per minute, or you need to administer 40 micrograms per minute. You need the same key pieces of information that we've already talked about. You need to know your desired dose. You need to know how much drug you have, how much volume you have. You need to know the concentration. And then the added piece that we just talked about is you need to know the type of drip set that you have. Typically, a 60 drop set, a micro drip is what we're going to use. So we'll go back to our lidocaine example. It's commonly mixed by adding 2 grams to 500 mils, and a typical lidocaine drip is administered at 1 to 4 milligrams per minute. So for this example, we will use 2. You can't deliver a range, so we have to start somewhere. So for this example, I'm going to start at 2 milligrams per minute as our desired dose. So you can approach this using a formula. The formula we already did. You can take the volume on hand, which was 500 milliliters. You can take the desired dose, which we said was 2 milligrams per minute. You can multiply that times the drip set that you have. That we're going to use a 60 drop set. And then divide that by how much drug you have. And remember, this has to be in milligrams. We put 2 grams in our bag. That means we have 2,000 milligrams total. If you do the math, that gives you your drops per minute, which is 60,000. You get rid of some zeros, that's 60 divided by 2, or 30. So you can see, you plug it in this formula. Now, I've said in other classes that I've taught that math is done differently by a lot of us. We all process these things differently in our brains. If memorizing this formula is an effective way for you to keep this straight, then do that. If getting familiar with the concentrations and the correlation to drips is a better way for you to do it without using a formula, then do that. The key is figure out what works for you, what makes sense in your brain so that you can consistently work through these problems and get to the correct answer appropriately. Because when you're doing this in high stress, low time situations, you want to be able to do it effectively and not get tripped up on the math. A simplified formula, and I say simplified with a question mark because not everybody thinks this makes more sense. For some people this is confusing, but if you know you're doing a dose per minute rate, your minutes in the formula is always 1. So using this formula, you're going to calculate the same sort of process. So in other words, the desired dose times the drip set over your concentration times the number of minutes gives you your drops per minute. Another method is the clock method. And again, this is one that for people who are visual learners, people who like a visual representation of this, some people prefer this, and it's quick and easy to do this on a piece of paper, on a notepad, and do this math, do this calculation. I personally like this method. I think it works really well. And what we're doing with the clock method is we're remembering, going back to what I talked about earlier about lining up the amount of drops that are being delivered with the amount of drug that's being delivered. So in the example of our lidocaine, if we have 2 grams or 2,000 milligrams that we put into a 500 milliliter bag, that concentration is 4 milligrams per milliliter. Well, earlier we said that 60 drops equals 1 milliliter. So if I deliver an entire 60 drops, you can see at the top in red, 1 milliliter has been delivered, meaning at that point, when I've given my patient 60 drops, I've given them 4 milligrams. If I only give them 30 drops, I've only made it halfway around the clock, and at that point, I'm giving them 2 milligrams. So I can figure out by the number of drops it takes how much drug I'm actually delivering. Each milliliter delivers 4 milligrams, and I can break it down from there. If I knew my desired dose in our early example was 2 milligrams, that means I want to give 30 drops in order to deliver 2 milligrams. So, kind of going ahead, that means that in order to deliver 30 drops and 2 milligrams in a minute, I have to watch 30 drops go by each minute. That's 1 drop every other second, roughly. Now, the way we set the rate is by counting. You need to have a watch with a second hand or a watch with something that counts seconds, because what you're doing is counting drips as they fall into that chamber next to you. If you can count 1 drop per second, you're delivering 60 drops per minute. In the case of the lidocaine example, that would be a rate that is going to give you 4 milligrams per minute. In the example we used with lidocaine, I don't want 4 milligrams per minute. I want to give 2 milligrams per minute, which means I want going half that rate. So I'm going to count 1, 1,000, 2, 1,000, I should see a drop. 1, 1,000, 2, 1,000, I should see a drop. If I wanted to give an even more conservative dose, we could slow that down. And now I'm trying to see 1 drop go by every 4 seconds. Now, once again, I'll say, be cautious with this. This is not precise. A number of things can vary this. A number of things can cause it to speed up or slow down. We're trying to count it, looking at a clock, counting it with seconds, watching drops go by. This is not a precise process. But in some settings where you don't have a pump available and you need to have some control over the amount of medication you're administering, this is considered a reasonable approach to estimate the amount of drug delivery. But please recognize this is not a precise process. And if you're using a number of the drugs that we use in the field that should be done in a very controlled fashion, such as norepinephrine or nitroglycerin if you're doing a drip and things like that, we really should be doing it in a more precise fashion, which means we really should be using pumps. Dopamine. So this is the drug I mentioned that isn't used as much, but I like using it for teaching medical math because I tell my students all the time, if you can do all of the parts and pieces of a dopamine calculation, then you can figure out any drug dose calculation that you're going to encounter because it requires each of the components. You need to do your desired dose rather, in dopamine. With dopamine, your desired dose is always going to be listed in micrograms per kilogram per minute. That means we need to know the patient's weight in kilograms. We need to know the drug concentration in micrograms per milliliter because that's how it's calculated. And we have to figure out our drip rate. If you get good at dopamine calculations, you can do any drug dose calculation, as I just said. So let's do an example. Your patient weighs 196 pounds, and you're going to start your dopamine drip at 5 micrograms per kilogram per minute. If you work in a system where dopamine is routinely used as a pressor agent for things like cardiogenic shock, this is a very typical starting dose. 5 micrograms per kilogram is a relatively safe dose that is likely to produce some positive cardiac effects. So we take our 196 pound patient, we divide that by 2.2, and we come up with 89 kilograms. Now, as you're working through the math, if you came up with 89 and say, I'm going to round this to 90 to make the math simpler, there's nothing wrong with that. For this example, we'll say 89 kilograms, and we know the dose is 5 micrograms per kilogram per minute. So we need to give 5 micrograms for every kilogram of their weight. So we multiply those together. And now I know that my desired dose is I want to deliver to this patient 445 micrograms each minute. That is my desired dose. So back to the common concentration we talked about, we put our 400 milligrams of dopamine in a 250 milliliter bag. We do the math, and that tells us that our concentration is 1,600 micrograms per milliliter. With that information in hand, we can now use our formula approach. And if you remember, volume on hand times your desired dose times the drip set you're using divided by the total amount of drug you have is going to give you your drops per minute. So here's the numbers that we just came up with. We have a 250 ml bag. We know our desired dose. We know we're using a micro drip because needs to be controlled precisely. And the drug on hand, that 400 milligrams with 3 zeros added, is 400,000 micrograms. So you plug those numbers into this formula, and what you're going to get is that I'll skip the description of reducing this here, but we're going to reduce some numbers here. You're going to get 17 drops per minute. So formula approach, this works, tells me that my starting dose for that patient that we just described is going to be 17 drops per minute. We'll do another method. So the clock method that I described, again, their numbers are up there at the top that we came up with. We know what our desired dose is. We know how much we have on hand, so we can plug this in. We know our concentration is 1,600 micrograms per milliliter. And remember, we know that 1,600, to give 1,600, I have to give the whole 60 drops. So you could go and enter the little numbers like I did before to figure out how much you're delivering. Each milliliter has that 1,600 micrograms. So in the case of this person, we said we wanted to give 445 micrograms per minute. Well, if 1 milliliter gives us 1,600, then 1/4 of that, or 15 drops, gives us 400 micrograms. So you can see that to get there, you're going to know that 800 would be all the way down there at 30. Well, we said 445. You can see that just looking at the clock, I can say, well, I'm going to go 400 plus a little bit more. To get to 450 is going to be right there around 17 drops per minute. So the clock is a great estimator to show you where you're going to be, because that's where you're going to hit to get that. But at a glance on the clock, I know where 400 is, I know where 800 is, I know I want 445 or 450 if you rounded it, which means I'm going to be around 17 or 18 drops per minute. I'll give you one more shortcut approach to this that a lot of people prefer. And if you're doing dopamine, the important thing to recognize is this that I'm describing only works if you have a 1,600 microgram per milliliter concentration. So we said 5 mics per kilogram per minute is our starting dose. Our concentration is 1,600 micrograms per milliliter. You take your patient's weight in pounds. In this case, we said our patient weighed 196 pounds, and you cross off the last digit. So you cross off that 6, and now we're at 19, and you start your drip rate at 19 drops per minute. This estimate with most weights will come slightly higher than that 5 micrograms per kilogram, but it's really close. So for instance, we said 17 drops per minute was 1445. Using that really shortcutted method that I just described, you got 19. You were very close to the same ballpark. I'll suggest that you can use this for a couple of reasons, or a couple approaches. One is, this is a quick, easy, down and dirty way to get in the right ballpark for the number of drops that are going to correspond to that. And keep in mind, this drip calculation, counting drops, is not a terribly precise way to deliver medication anyway. The other thing is, it's a nice way to double check your math. If you're looking at a national registry test question or something that's asking you to do these calculations, and you know that for dopamine at the appropriate concentration, a 195-pound patient gets 19 drops, and you did the math, used the formula, and came up with 38, it's a good catch for you to realize I've got half or double what I'm supposed to. I need to go back and take a closer look at this. So at least it gives you an idea of how to get into the ballpark. With each of these methods that I've talked about, I encourage you to go through and practice different drug calculations, practice different scenarios, plug in different dosages, different weights, practice doing this process so that you become comfortable with it. I also strongly encourage people to use references. What I just described may be critical if you're taking a test where you're not allowed to use references. But when it comes to field care and things like drip rate calculations, we really should be using printed references, printed resources, digital resources, some sort of reference tool. So when 3 o'clock in the morning you're trying to do this math, you're not relying just on your memory or your math skills, but you have a way to quickly access that for this patient's weight with this drug and this concentration, I'm going to set it at this drip rate. That math can all be done ahead of time, and every one of us that works in EMS should be carrying those tools with us so that we're not reliant on this math. Thanks, and I hope that helped.